No, here is online now because we
Online?
have an increase of the COVID cases. So the campus is almost closed.
Okay. And Italy,
Italy is a hybrid.
hybrid solution.
Yeah,
Okay.
but
So
also depends on the university and region because we have different rules in different regions.
yeah.
So it depends on the increase of the cases in the
Okay.
places, and they will decide. They usually decide accordingly to the numbers that they have. So
Of course.
So we can start because the time
Okay.
is scheduled.
Okay. Okay.
So let's start the third session of the IGF26, and welcome to our conference. And it is the first time that I do the chairman in an hybrid session. Please help me saying the time. We have
Okay.
an invited lecture and nine traditional presentations. For the invited lecture, we have 30 minutes. I think we can use 10 minutes for a refresh of the presentation and 20 minutes for the discussion. For the other presentation, please stay in 2-3 minutes of short presentation and the rest of time for the discussion.
Okay.
It is my pleasure and is my honor to introduce the Professor José Antonio Correa of the University of Porto, Portugal, who told us about the fatigue strength modeling in the global and local approaches. We know the importance of fatigue in our field because it is much more than 200 years that we study. Professor Correa, in its review, starting from the beginning models up to now, explain us the new approach of the fatigue and results of the research. Please, Professor Correa, please.
Okay. Thank you. My name is José António Fonseca de Oliveira Correia, my full name. Okay. I'm here to present, and of course, I'd like to say that for me it is an honor to stay here and to accept the invitation to make this plenary session. And I'd like to say that I am a senior researcher at INEGI and Construct, University of Porto, and also invited professor in various universities like University of Porto, University of Coimbra, and Delft University of Technology. So the idea is to do to make an overview about fatigue strength modeling, because we have a lot of models, and here I'd like to show some models to be used in global and local approach. I'd like to show that University of Porto is located in Northwest region. I know that Roman know very well this region because in the past was occupied by the Roman Empire. So here we can see the Faculty of Engineering of the University of Porto. We have several research centers. That of course depends of the research area. We have different kind of research centers, and I am working in Construct and also in Laieta, where is placed the INEGI. So after that, I'd like to show that the University of Porto, Faculty of Engineering, is organized in several research centers and also in institutes of interface between academy and also industry. Here we have the industrial partners or industrial partners, and also here we have a spin-off that were created by the academy in cooperation with industry. So my presentation, I'd like to present some topics that are relevant in my research activity. Here I'd like to show that we have different kind of relevant aspects to fatigue design and analysis of metallic structures. What are the main factors influencing fatigue damage? What are the global SCN approach and also local approach that we can use in our analysis? Here I introduce same topics such as low cycle fatigue modeling supported by strain energy density based Huffman model, considering the variability of dislocation density to estimate the strain life parameters, and other perspectives on the generalization of Stussy full range fatigue model for various fatigue damage parameters, and also how we can generate a new fatigue model covering very low cycle fatigue, 2 gigacycle fatigue regimes for high strength steels. And finally, a simple summary. So here, I would like to say that engineering structures are designed for high cycle fatigue regime, and it will be important to introduce other kind of regimes, because same of collapse cannot justify it only to use design rules for the high cycle regime. Here it's important to know that we have different kind of aspects relevant to do the fatigue analysis and fatigue design and analysis. We have certainties like structures will age, and of course we need to develop solutions to improve the fatigue life of bridge, offshore pipelines, wind turbines, etc. And of course we have also uncertainties like fatigue loading, structural response, resistance to failure, and for example the fatigue behavior of old steels that were used or that were in operation in old steel bridge. So we have different kind of research aspects that are important for the international scientific community, like fatigue resistance of elevated connections, bolted connections, to study different kind of fatigue regimes, how we can make the probabilistic fatigue and fracture approach, the combination between different kind of phenomenon, fatigue, corrosion, etc. So, and of course, we need to develop the rules to be included in the codes to be applied by engineers. So, as you can see here, the fatigue is important, is relevant for the infrastructural domain, and also for the offshore domain, oil and gas, industrial buildings, etc. We have a different kind of structures where the fatigue phenomenon is relevant. I would like to move on for the global SN approach. How the global SN approach are presented in the code. So we can see here that normally we have a curve to represent the finite life, and we have the conventional fatigue limit. Normally we can see here the equations that are included in the codes to be used to do the fatigue damage assessment of structural detail. Here you can see different kind of models from Wöhler, Baskin until now. Not all models, but the idea is to show that we have models that were developed to describe the fatigue life, finite fatigue life regime. We have models to describe the finite fatigue life and high cycle, well, considering the conventional fatigue limit. We have full range models covering all fatigue regimes. We have different kind of proposals, but all these proposals are given as or are using the fatigue damage parameter, that is the stress. So we have also local approach divided into 3 categories: stress, strain, and energy. Normally, these local approach are used to model fatigue crack initiation. We have different kind of local approach. as I told before, based on stress, strain, and energy. Here you can see same models that was developed by Baskin, Morrow, Coat-Vechet. Coat-Vechet cover all fatigue regimes from quasi-static until fatigue until high cycle. Here we can see that we have also proposals from the literature to use the strain as a parameter. Well, here we can see the Coffin-Manson-Morrow relationship, the Smith-Wesson and Topper proposal, and also the Morrow relation introducing the mean stress effects. So here we can see same results applying strain damage criterion and also the Smith-Wesson and Topper parameter. Here we can see the results for the strain life parameters. So recently, Karunananda introduced a new perspective that we can also use or adjust, use the Coat-Vechet model to local approach. And here, the first work was done by Karunananda that introduced the strain parameter in the Coat-Vechet equation. We can see that here we have the equation Coat-Vechet model using the strain life parameter. Of course, we can do the same using the Smith-Wesson Topper parameter, and the same was done. Here you can see the parameters, the variables for this equation. That is a kind of generalization of the Coat-Vechet model for various local fatigue damage criteria. We have also local approach based on energy that was developed firstly by Elin, for example. Here you can see the equations proposed by Elin to describe the amazing material, non-amazing material, and here you can see the combination between the elastic and plastic part using the energy. So we can do the same, and we can generalize the Coat-Vechet model also to the strain, to the energy parameter. So after that, here we can see a kind of generalization of the fatigue Coat-Vechet model for several fatigue damage parameters. Okay, the work was published, and we can use different kind of parameters to describe the local fatigue to do the local fatigue model. Of course, it is important to this kind of models because the designers and engineers would like to have access to a curve to apply in same applications, engineering applications. So we can, of course, evaluate the parameters for the generalized Coat-Vechet model. Here you can see the parameters of the Coat-Vechet model applied to the pressure vessel steel. You can see the variables, and you can see the fitting here in this figure. The same can be done for the strain parameter and also for the strain parameter for the same material. And here we have the results, and you can see that considering the fatigue data and also the monotonic results, we can make a kind of fitting to represent a full range model based on Coat-Vechet proposal. The same can be done considering the Smith-Wesson Topper parameter. You can see here, and also we have the results. So I'd like to introduce two new research lines. Here, the idea is to, okay, we have different kind of models to make low cycle fatigue modeling, and here we are using the strategy that was firstly proposed by Professor Glinka, and after that we have different kind of researchers like Uffman, Picker, and other researchers that introduced a new concept that okay, we can, for example, propagate a crack considering successive crack reinitiations. So, but okay, same models allow us to evaluate the strain life parameters like this. The model that was developed, that was proposed by Uffman, based on strain energy density. So here we have three methodologies that were proposed. The first methodology is based on the proposal from the Uffman model, where the critical dislocation density driven by the highest strain amplitude. The second methodology, okay, why not use to the mean value of the dislocation density? And after that, okay, why not to apply a stochastic prediction considering the variability of the dislocation density and also cyclic strain hardening coefficient. So here we have the different still that different materials that were used in this analysis and the variable, the parameters for the values for the parameters, cyclic, elastoplastic, and also for the strain life parameters. Here we have the experimental results where the Coffin-Manson-Morrow equation is also presented. Here we have the methodology that was proposed by Uffman that is using the strain energy density. Okay, here we have the elastic and plastic part, and this model was proposed by Uffman that is using the critical dislocation density. So after that, based on this model, it's possible to generate the strain life parameters, and you can see here how can do it. Okay, and then we can also estimate the dislocation. Okay, dislocation strain, the critical strain dislocation density, based on this equation, of course, from the application of this model. Here we have the results applying the model that was proposed by Uffman and considering the strain, considering the critical strain energy density obtained for the highest strain amplitude. Here we have these values, and of course we have here the strain life parameters estimated based on these values. And here you can see for different kind of materials and the consideration and in this study. So the second strategy was the following. Okay, why not evaluate the stress, the dislocation density for each experimental test? Okay, because according to several authors, we have different kind of values for different kind of strain range. And it was then, okay, we have this value for each specimen and the mean value. The same was done for other materials, this aluminum alloy, and also for this aluminum alloy. And then we can see the results that we can consider that the fitting is very interesting. The last methodology is okay. Why not to apply the Monte Carlo stochastic prediction? The idea is to consider the variability of the strain, the dislocation density, and here we can see the approach. Okay, that can be used. After that, we will use inputs that we'll consider it as a variable, as a variable variability parameter, and also we have other parameters that was considered as a deterministic variables. After that, the Monte Carlo stochastic simulation was applied, and the output was obtained for the fatigue strain coefficient and also for the fatigue ductility coefficient. And after that, we can also evaluate the mean value for the parameters, for the strain life parameter for each material. Here we can see the estimation. We can see the output, the results, and also we can use this methodology to make a kind of probabilistic modeling, probabilistic prediction, okay, for the strain life fields. Here we have a comparison for different for the materials that was considered in this analysis, different aluminiums alloys, and here you can see that in all the best methodology is to use the Huffman model, but considering the variability of the dislocation density. I would like to show also that it's possible to generate a kind of Stussy full range model for different kind of local parameters. Here we can see that the proposal that was proposed by Stussy. Okay, here you can see the equation, and we can see the curve in this figure. And why not to generalize and do the same that was done by me with the coefficient model. And here we have a proposal for different kind of criteria: stress, strain, and energy. You can see here the proposals. Of course, this research line is ongoing also. And finally, I would like to show you a model that can be developed to cover from very low cycle fatigue to giga cycle fatigue. Different kind of was considered different kind of assumption from Fluia and Paulino, and also from Pittel. Here we have the results from Pittel for the high strength steels, and after that the idea that was proposed by Pittel, and now we have a equation, a double logistic fatigue model to describe this proposal for the high cycle strength steel that was indicated by Pittel. Here we have a proposal. Of course, it is a phenomenological fatigue model, but it is important for the community because we need to make a mix between the surface fracture mechanism and also internal fracture mechanisms. Is important to the designers and the engineers and to be included in the goals. So, and finally, I'd like to say that this analyzed coefficient model for several fatigue damage variables could be considered a significant enhancement towards for the fatigue assessment of structural details. A proposal to generalize of the generalization of the Stussy fatigue model for various fatigue damage parameters and generalized coefficient model seems to be suitable for engineering structures, considering that the number of cycles of failures of these structures cannot be explained only for the high cycle regime. Okay. And the low cycle fatigue modeling based on Huffman approach using the strain energy density and considering the variability of dislocation was investigated and discussed and seems to be the best way to use the Huffman approach. And finally, I'd like to say thanks for your attention, and sorry for the time that I have taken.
Thank you very much, Professor Correa, for your presentation. The time is quite finished,
Yes.
but we have a few minutes for the questions. Are there any questions?
Yeah, I have a curiosity, if I can.
Please, Filippo.
Yeah, so for first of all, thank you for the nice presentation with the very good overview of local and global approaches. I would like to ask you an opinion about hotspot methods, which is a kind of intermediate approach between local and global. So I
Yes.
want to understand a kind of opinion that you have about these approaches that in the standard are quite present due to the fact that UK is pushing a lot with other countries to have these standards in place. So it's nice to hear your opinion about this.
So my opinion about the hotspot stress approach. So I think that is not the better way, okay, but is easy to use by the engineers and the designers. Of course, the hotspot stress is a kind of hybrid method between the global and the local approach. And my idea is not the better way, but is easy for the designers and the engineers. And of course, we can discuss what I think that the concept is interesting, but not in the format that is included in the codes. Okay, and maybe a kind of review of the hotspot concept. I think that is more important to talk in hotspot concept because allow us to use local approach, and we can see what can happen. Okay, because normally this approach is used also to the welded joints, and of course maybe the way can be, for example, use local approach and considering the residual stress effects due to the welded joint that we have. I think that, in my opinion, okay, we need to make a kind of review about the hotspot concept. I think that is better to call hotspot concept and not hotspot stress, but okay, the literature is talking in hotspot stress, and why not use the local approach and then consider the residual stress effects in the welded joint. So of course we have different kind of criteria, and the strain energy density seems to be also a good criteria to be used in this kind of connections.
Yeah, thank you so much for this.
Thank you.
Thank you. Other questions from the colleagues? No, just a curiosity by me. I see now your slide where you show us the new fatigue model covering very low cycle fatigue to gigacycle. Yes. It's my consideration. It's a very dream for us to have this kind of models covering all the real fatigue case. But my question is about the criterion used in energy density. I see the formulation, and my question is which the mechanical energy in this case can or cannot interact with the chemical energy, for example, in stress corrosion fatigue.
Can you repeat, please, again, your question?
Sorry, my question is in the models who use the energy density as a criteria, okay? Which is the way to correlate the chemical energy which interacts with the mechanical energy in case of stress corrosion cracking or corrosion cracking, normal corrosion cracking.
If we can do it, yeah, it is your question. Yes, it is your question.
Yes, the question is, there is a way to correlate both the energy. This is
maybe I don't have a lot of research in this field, of course. Maybe we have a correlation between the corrosion phenomenon correlated with fatigue, of course, and we can consider the energy also in this kind of approach. We can, I think that we can do it. Okay, but this kind of approach need to be applied, well, considering the knowledge that I have in this Huffman approach, based on strain energy density. I think that we need to analyze very well how I can consider, for example, the critical dislocation density, because we have a different values from the experimental assessment, because we can estimate this value from the literature. We have different kind of models to estimate this parameter, and we need to pay attention. Of course, the corrosion process we will affect this parameter, dislocation density, and of course we can consider also the impact of the corrosion process in this approach. But as I told you before, we need to pay attention because we have different values when we are using, for example, the strain life data from the tests, fatigue tests. We can, of course, estimate this parameter from the fatigue tests for each strain amplitude level. But if we will evaluate according to several methodologies that we have to estimate this value, looking to the microstructure, level, we will obtain a value that will be very lower or very higher when compared with the value that we are estimating based on this approach. And we need to pay attention, and we need to understand or to introduce here these kind of effects, because according to the literature, the values will be very different. Of course, we can introduce in this approach the corrosion process. Okay.
Thank you for the answer. It's my opinion that for all the fatigue regime, we can find a correlation, but in gigacycle we cannot.
Yes, we cannot
find it.
Cannot do it. Yes,
because the initiation is not on surface, but
yes.
inside the material. If the corrosion is not so hard, it's very hard to have a correlation between the energy.
Yes, and these kind of models are driven by the plasticity. And when we are in gigacycle, we don't have. Of course, in micro level, we will have. Okay, but it is other kind of other kind of things. Yes, of course.
Thank you very much, Professor Correa. But the time.
Yes. Okay, thank you.
Thank you very much. And just a moment, I find the first presentation. We have 10 minutes, 2 minutes for the short presentation from Riccardo Gaivano, Andrea Tridello, Davide Paolino, and Filippo Berto. Defect-driven topology optimization, top FAT algorithm extended to commercial software for wide-ranging applications. Please.
Hi, good morning.
Riccardo Gaivano.
Yes, I'm here. Good morning to everybody.
Please.
I'm going to share my screen in a moment. So, good morning, everybody. My name is Riccardo Caivano, and my colleagues are Dr. Andrea Tridello, Professor Davide Paolino, and Professor Filippo Berto. We are going to present our research about defect-driven topology optimization, especially the extension of the top FAT algorithm to the commercially available software HyperWorks for wide-ranging applications. So basically, topology optimization is one of the most employed design methods for additive technologies. However, additive products suffer from a consistent defect population, and often it is not negligible. And this defect population lowers and drives the fatigue response of the IM parts. Here, for example, are displayed some typical process-induced defects, such as pores, cluster of pores, lack of fusion, or improper layer bonding. So the defect presence and the related fatigue limit must be included somehow in the topology optimization algorithm in order to have safe and reliable designed parts. In the literature, an algorithm already exists. It's named TopFat and is able to include the defect analysis in the topology optimization framework using the Murakami model. However, the original TopFat algorithm is written as a proprietary MATLAB code, and so its extendability to real and complex industrial cases is limited. Therefore, in the present research, we aim to extend this TopFat procedure using the commercially available software HyperWorks to unlock wide-ranging application both in the industrial and the academic field. So that's the aim of our research. Okay.
Thank you very much for your introducing. And any question from the colleagues? No one? I have a curiosity. How you optimize, for example, the mesh in your problem in presence of singularity of the geometry? Because often when you have to optimize, you have to, please, can you hear me?
I think there is a little, yes.
Okay, my
So
question
can
is...
Can you repeat the question? Like in the communication.
Can you hear me?
Yes.
Okay, my question is how the optimization model can work in singularity of the geometry.
So
often you have
basically the idea. So basically the idea is that the Murakami model impose a limit over the first principle maximum stress within the domain. And if we evaluate this limit using the Murakami model, we are able to impose this limit over the first principle maximum stress in the topology optimization, which is already implemented in the HyperWorks software. So is the in the case of our research, so the extension of the TopFat algorithm to the HyperWorks commercial software, the singularity problem is managed by the topology optimization solver within the Altair suite. Instead, in the original TopFat algorithm, which was developed using hybrid elements, this problem was solved in a slightly different way. So mixing the finite element formulation between an hybrid displacement and stress formulation. And so the singularity was managed in this way. I don't know if I answered your question.
Okay. Yeah. It's thank you very much. I catch that you have no equation to minimize. You don't use the derivative for the optimization process. Is correct?
No, we use essentially when we extend the algorithm, the TopFat algorithm, to the commercially available software HyperWorks, the derivation is inside the commercial software, and that is the key part.
The formulation is inside of commercial software. This is the
exactly.
The answer.
It's not.
Yeah. Okay.
Exactly.
I think
it's
it's
not
a
in the original
way.
Exactly. Instead, in the original version of the algorithm, which is implemented in MATLAB, we wanted to minimize the compliance. And the derivative is made with the material distribution raw, which is the design parameterization of the algorithm. So this is the original formulation of the top fat algorithm. However, in order to have a good extent and also for people which is not likely to use this type of minimization problem, and especially for industrial cases, the idea that all this stuff, all this mathematical programming, design parameterization, sensitivity analysis, derivation is made within the software can unlock the possibility to use the defect-driven topology optimization also for industrial people and industrial cases, which is not maybe so practical with this type of mathematical program, as I told before.
Thank you very much. And thank you, Ricardo. And next presentation is numerical investigation of, thank you to you, of pentamodes crack propagation. Professor Panagiotis, are you ready?
I am Panagiotis.
Thank you. Please.
So, one moment. So, hi, I am Panagiotis Mberopoulos, and I'm going to present to you our research numerical investigation of pentamodes crack propagation. My co-author is Evstathios Theotokoglou. We have performed a mode 1 crack propagation testing. We have used a typical pentamode structure like this, and we have used this testing specimen with these dimensions, and we have some pentamode properties that can be found here. And we have used titanium for bioengineering purposes, and you can see also its properties. We have performed a small and large displacement analysis, and we have compared with some experimental results from the work of Hedai et al. And as we can see, in the linear region, we have very close results to the experimental, but after the 0.5 displacement, we have larger values for the force that we see in the crack tip. If we use the large displacement analysis, we see that the results are more close, but we have also large percentage difference. And here are also the results that I have told you. And thank you.
Thank you very much. The discussion is open. Any question?
Yes. Hello.
Please, Marco Maurizi, please.
Yeah, nice to meet you. Thanks for the presentation. Just a curiosity, which are the geometric parameters that you varied of the structure?
Please repeat.
Which are the geometric parameters that you varied of the structure?
So, as you can see here, we have our testing specimen. It is constant for all the three cases, and we have altered the properties inside. I mean, we have altered the properties of this bubble inside, as you see here.
Yes.
Yes.
Okay.
It is the power that we have altered.
Okay, so you control the porosity basically,
yes.
Right? Okay.
Yes, exactly.
Got it. Okay. Thank you.
And
may I ask a question, Mr. Chairman?
Please.
May I?
Hi.
Please do. Hi, Stavros.
I am not very familiar with these modern materials.
Mm-hmm.
Would you characterize this class of materials as isotropic or anisotropic?
These materials are anisotropic. We have seen that if we compress them, they can also turn, they have turns. If they have large Poisson ratio, they are not isotropic, for sure.
So in this context, if I have to determine experimentally the mode 1 fracture toughness,
yes,
I suppose that the orientation of the specimens would play an important role. Have you considered such a parameter? So there is not one fracture toughness mode. It must be a number of fracture toughnesses.
This is for future work because it's a very wide problem, and yes, we have to test in more cases to be sure.
Have you some data from literature concerning?
Yes, this is
how many fracture toughnesses do we have for such materials?
Yes, we have performed from literature, yes. Mm-hmm.
Thank you.
You're welcome.
Thank you. Other questions? Just one for me. In the second slide, I see a sort of a cell parameter A, which is the A dimension.
Can you repeat? Yes.
The A dimension.
Yes.
Of the cube.
Yes, yes, I see. Yeah, it's the main dimension for the pentamon, and it is related to the porosity.
Yeah.
Yes. So we have.
Which is the order of these dimensions? Microns, nanometers,
micrometers.
Micrometers. Okay.
Yes, and in the sketch it is millimeters.
Yeah. Yes. It's a values, very high values. You have to perform a very teeny crack in order to get a real fatigue propagation, curve propagation. Okay. Another, my curiosity, why the model works much more better in low deformations?
In large deformation,
yeah.
We haven't used the material that we have used it linear, so we don't use a plastic deformation curve. Mm-hmm. And after the 0.5 millimeters displacement, we have some micro crackings, some microplasticity that we haven't taken care of them.
Okay. And when you generate the plasticity,
yes,
the number of dislocation and defect due to the plasticity were born inside the cell, or it's a phenomena who involve the wall cube as you show in the slide 2.
Can you repeat, please?
The defect generated by the plasticization, which is the dimension of these defects.
Yes.
The order of the microns or nanometers, I don't think nanometers.
As I have said, we see the larger percentage difference after the 0.5 millimeter displacement. We haven't tested this type 1 crack propagation with plasticity curve, but I think that if we do this, I can be more specific to give more specific comments about this.
Okay, thank you. Thank you. Compliments for your work.
Thank
But
you.
the time is finished. You have to proceed with the next presentation.
Okay, thank you.
Thanks, Panagitios. And sorry for my pronunciation. Because
Don't worry, don't worry. I can understand.
It's Greek to you, Vittorio.
Thanks, Professor Kourkoudis. And the next presentation is notch effect in the tensile and compressive quasi-static behavior, or 40% short glass fiber, PPS reinforced composites, by Meneghetti, Ricotta, Sorgato, and Zappalorto. Who is online?
Yeah, yes, I am. Thank you very much, Mr. Chairman. I tried to...
Ciao, Mauro.
Ciao, ciao. I tried to share my presentation. Okay, I think you can see. It's right?
Yes.
Okay, thank you. Good afternoon to everybody. My name is Mauro Ricotta from University of Padua. The other authors of this work are Professor Meneghetti, Professor Sorgato, and Professor Zappalorto. In this work, we have investigated the static behavior of 48% short glass fiber reinforced PPS matrix in order to provide new experimental results useful for engineers involved in the structural design with this kind of material, and in order to understand the effect of the stress concentration, the loading condition, and the fiber orientation angle on the damage mechanisms and the overall strength of this type of material. And we have found that quasi-static tensile, and we have carried out, quasi-static tensile and compressive tests on plane and notch specimens. The main results that we have found are as follows. Concerning the plane material, the compressive static strength of 0 degree, 90 degree specimen was 1.33 and 2.5 times higher than the corresponding tensile strength. And thanks to the matrix utility, during the compression test, the final failure was controlled by the shear stress acting on the matrix independently on the fiber orientation angle. In the tensile specimens, different damage mechanisms were observed depending on the fiber orientation angle. While concerning the notched material, we have found that, as we can expected, the larger the notch radius, the higher the static strength is for both the orientation angles. Under tensile loading, both for 0 degree, 90 degree orientation angle, an incomplete notch sensitivity was observed. And finally, under compression loading, for both the orientation angle, the final failure was found to be controlled, but the shear stress acting on the matrix justifying the observed notching sensitive material behavior. That is all, and thank you very much for your kind attention.
Thanks, Mauro. Is there any question?
Yeah, I have a question.
No one?
Yeah.
Please, Filippo.
Yes.
Please, Filippo.
Thanks you for the nice presentation. I would like to ask if the size of the samples, so if the size effect can influence your results in terms of amplification of the compressive static strength at 0 and 90 degrees with respect to the corresponding tensile strength. So it's only a curiosity if you think that that can be a parameter that can influence the final results of, or if these results is quite stable according to the size.
Okay, Filippo, thank you for your question. Here, you can see, you can see the size of the plane specimen that we have tested under compression load. Of course, the specimen where, you know, the free length was very small, 10 millimeters, and the thickness of the specimen was 4 millimeters in order to avoid buckling during compression tests.
Okay.
And here I'm sorry, just a moment. Here you can see in the, when I move, okay, in the,
yeah.
here you can see the size of the specimens that we have tested during the compression test.
Yeah.
Of course, also in this case, the length, the free length was very small, and we are confident that our results are quite stable.
Okay.
With respect to the size that we have tested. Of course, there is probably some influence of the
of the gripper area.
the boundary condition, because the distance between the boundary condition and the net area is a little bit sufficient to avoid a very strong effect of the boundary condition that we are applying.
Yeah, thank you so much. I understand. Thank you. It's a very good explanation. Thank you.
Thank you, Filippo.
Thank you, Mauro and Filippo. Are there any questions? Just a curiosity, how you take into account the interaction between the matrix and fiberglass in your material?
Okay, the interaction, have you seen?
Yeah.
Okay. We have sorry. Okay, we have tested specimens that we matched from injection molding plates, and our point of view was does not take into account the microscopic behavior of the material. We have tried to apply classical finite linear elastic fracture mechanics without taking into account any interaction between fabric, matrix, and fiber, because we have chosen this point of view. We know that there is, of course, our results cannot be extended to different kind of material, because the interaction between matrix and fiber is fundamental in this kind of in the case of short fiber reinforced composites. Therefore, our results can be used when we are working with this specific material. But we have tried to avoid the modeling the fiber matrix interaction in order to design a very simple engineering based tool to design structure loaded in the case of when the applied load are static loads. Probably the influence of fiber and matrix interaction is more important in the case of fatigue tests. Fatigue loading is very known by the literature, but in the case of static load condition, the influence is the static strength, of specimen is mainly controlled by the geometric effect. That means is mainly controlled by the size and the shape of the notch more than the fiber and matrix interaction. But at the moment, we cannot, extend our results for different kind of material, because we have just tested this particular fiber matrix interaction that is correlate to the material that we have analyzed.
Thank you very much, Mauro, for your answer. I think is a very good model for design the components, mechanical components. This approach. It is not so good for design the material in order to optimize the material.
Yes,
but for the components, mechanical components is perfect.
Yes, I totally agree with you. We have tried to develop a tool to design the structure, not the material. We have to know the strength of the material, the fiber fraction material. We have to know a certain number of input data in order to use this kind of approach that is tough just for design the structure, not the material, as you can said. Thank you.
Thank you very much. Thank you very much. And the time is finished. I have to
Yes, of course.
present the next presentation. Thanks, Mauro. The next presentation is entitled Mechanical Properties Prediction of 2D Interlocking Structures Using Deep Learning Methods. Authors are Marco Maurizi, Ciao Gao, and Filippo Berto.
Yes.
Who is the presenter?
Yeah, I'm here. So hello, everyone. I'm gonna share the screen.
Thank you, Marco.
Can you see the screen? Yeah, just a brief intro. I have just one slide where I try to summarize the work we have done. So just follow my pen. Anyway, so we have the idea of this paper is we start from some observations in nature where we know, for example, here just report an example, that in some biological systems we have some peculiar geometric features. In this example report is the famous diabolical beetle, which has remarkable mechanical properties. Specifically, it has high toughness, and this toughness, as is shown here, is so the authors from this paper, they argue that probably is from an interlocking features between the two parts of the elytra, which is this part on the back of the beetle. And starting from this observation, this is just an example that in which we have really remarkable mechanical properties like stiffness or toughness, and we created, like we wanted to apply a deep learning method to predict the mechanical properties of generic interlocking structures. So here you can see in this part a generation of the geometry that we consider. So it has two phases, the black and the gray phase. And so we use a kind of cellular automaton-like approach for generating these kind of structures. And they are simply two phases, the black and the gray, under uniaxial tension. And so from this structure, we applied, thanks to recent developments in deep learning models and approaches, we applied these methods, and we predicted, we assessed the mechanical properties, which are in this case the stiffness at initial slope, and the strength as the peak of the stress strain curve, and the toughness as the area underneath the curve. And then, as you can see here, some results. Here we have the prediction. So a comparison for the geometries outputted from the finite element model and from the deep learning model. As we can see, so for strength and toughness, we have the high-performing geometric patterns that are well predicted by the deep learning models. You can see here. So we have this pattern for the high strength geometries, and this kind of patterns for the high toughness. And so the other point of the work was to understand, was to prove that we can use a kind of transfer learning from smaller design space. So let's say from a 10 by 10 design spaces, you can see here, to predict a 2020, for example, as in this paper, design space. And so and then I put this this double arrow to say that we can use, for example, in the future, transfer learning to deduce in this direction, to check if the biological systems have optimal mechanical properties or not, and try to understand why. And and this is one of the possible side effects, let's say, of this research, is to understand why the evolution has generated this kind of peculiar features. So yeah, and so these are the main points, the highlights of the present paper. So prediction in a fast, accurate way, the mechanical properties of this structure. And then we can use transfer learning with accumulated knowledge to predict these properties and on larger design spaces. And we can enlarge design space compared to analytical models already present in literature. And as I said before, possible side effects is to understand why nature developed such structures. So thanks. If you have some comments or questions, thank you so much.
Thanks, Marco. Are there any questions from the colleagues? No one? I have a curiosity. The dimensions of your patterns is around 100 microns.
So the size is, in this case, for example, it's a 10 by 10. So here is just a 10 by 10, but let's say we used it's a 10 by 10 millimeters, let's say, but this is, it doesn't, like the approach is not limited to the size, it's just an example. It can be whatever size. You can use also micrometers, of course. Yeah.
Because I see in the Diabolicus bag the interaction of the patterns is around 100 microns.
Yeah, exactly. So, but this is was just an example to explain that we start from the observation from these systems, but this is just an example.
Which is the formulation of the material? Is elastic plastic material as you
it's elastic bilinear plastic.
Which are the parameters do you use in this simulation?
So I can show you. I have
elastic modulus and.
Here I have some details of the P model. So I use an elastic modulus for gigapascal, 0.3 for the Poisson ratio, and for the ES 20 megapascal. And here some the properties I use for the damage initiation evolution.
But these are just one cell or a lot of cells in contact?
Okay, here there are the two phases, the black and the gray, and there is contact between this in this way, right? Yeah. So there is contact between the gray and the black phase. Just contact, mechanical contact.
Yeah. Mm-hmm. Okay, thank you very much. Yeah. Are there other questions? We have a time, just another curiosity. Yeah. The friction column model you use mi equal to 0.1.
Yes.
Why you use this kind of values?
So
0.1 is not so high.
Yeah, sure. I mean, these parameters are just, let's say, we could have used also other parameters, but so we saw that the influence in these specific geometries of the friction coefficient is not so important, while in other cases where there is pull out, for example, in the work of Bartelat, in which the shape of the interlocking is there is pull out of the two parts. So in that case, the friction coefficient is more important.
Oh, thank you very much. And the last curiosity is the model takes into account just the static phenomena, because in dynamic phenomena you have to take into account the inertia, the other kinds of forces born at the contact.
Yeah, of course. This is static. Yeah, it doesn't take into account the dynamics.
And the temperature changes and, during the friction, and this is much more complicated. Okay.
Yeah, but
thank you.
Okay, just we wanted to investigate. So without taking into account the mass and the inertial effects, since it's just more, let's say we can say it's a structure, but if we downscale like in the beta I showed before, we can consider also like a material feature. So you can consider as material properties somehow. if we go down to the scale.
Thank you very much, Marco.
Thank you.
And next presentation is entitled An Effective Modeling Approach Based on the ELE, ANLE, and M integral for simulating crack propagation and thermomechanical loadings. Authors are Domenico Amendola, Fabrizio Greco, Paolo Lonetti, and Arturo Pascuzzo.
Domenico, I am here.
Please, Domenico.
Okay, I share my screen. Okay, can I start?
Please do.
Okay. So, good afternoon, everyone. I'm Domenico Mendolead, and I am a PhD student of University of Calabria. And the work that I'm going to present is co-authored with Professor Paolo Lonetti from Fabrizio Greco and Arturo Pascuzzo. So, in this work, we present an efficient finite element modeling approach to simulate crack propagation in a linear elastic continuum media under mechanical, thermal, or Vogel loadings. So, the proposed methods combine moving mesh approach based on the ALE formulation for handling random raw cracks easily, and the interactional integral method to extract fracture variables at the crack front. So the method is managed by an automatic algorithm. The moving mesh moves the crack to simulate the propagation, and this movement must not change the shape of pre-existing crack. So for this reason, is defined a small stretch segment near the crack tip to describe the instantaneous propagation. So the sieves at the crack front are extracted utilizing the MA integral and used to evaluate the crack set condition, crack set condition and propagation direction. During the propagation, the elements around the crack tip distort because of the motion of mesh nodes, and the remesh process are required when the mesh regularity is compromised. Finally, a tolerance angle of this stretch segment is posted with respect to the local crack system, and when this tolerance is fulfilled, the geometry and the computation node are updated. So the proposed model has been validated by comparison with analytical solution and the prediction of other numerical methodology. For example, we have here we have the results of a rectangular plate with an inclined central crack subject to a uniform vertical temperature gradient. We can see the results obtained in terms of dimensional sieves, and these results converge quite well with the analytical value of Murakami. So in conclusion, this work has shown that MA integral can work accurately in the framework of the ALE methodology. And in the upper, we can see in the mesh frame evolution and the cofaction. Okay, thank you very much for your attention.
Thanks, Domenico. Are there any questions?
Sorry for my English.
Oh, it's perfect. Don't worry. And Domenico, can you show us the slide number 2?
Okay. I don't understand. Yeah. I don't listen.
Can you? Okay, I see the schematic procedure. The analysis is managed by an automatic algorithm. Can you tell us some details about this algorithm?
Okay, so now the analysis, for example, start defining geometry mechanical property, and the boundary condition. So we say that the Halle move the tip. So the initial crack is a polyline that start from the external boundary and develop up the crack tip. Now the Halle moved the crack tip to simulate this propagation, and this movement must not change the shape of persisting crack. And for this reason, it is at an extra node near the crack tip and near the crack tip, okay, and thus give this a stretchy segment, and this stretchy segment will stretch during the propagation. When the geometry is built, the computational mesh domain is created. Now, at this moment, the load increase slowly. At each step of load, the stress intensity factor are extracted using the HEM integral and utilizing the HEM integral. And the sieves are utilized to extract the sieves. And these sieves are used to evaluate crack onset condition and the propagation of propagation direction. So, we use a classical fracture criteria to reproduce the crack onset condition and propagation of direction. We use the maximum circumferential criterion stress. So when these conditions are fulfilled, the crack starts. The crack starts, and so the crack starts, and okay, the crack starts, and for example, due to the movement of the crack tip, the elements around the tip distort and distort, and so the program required our remeshing process. So in the present model, the mesh distortion is checked through the non-negative first invariant of the isochoric Greer-Lagrange strain relative to the mesh frame. So the remesh takes place when this invariant is bigger than a suitable threshold. And very important to say that this possibility to manage the mesh frame distortion at each step of the analysis help to reduce the procedure of remeshing and help to saving relevant computational resource. However, a tolerance to the angle variation of the stretching segment with respect to the local system is imposed, and when this tolerance is fulfilled, the propagation stops, and the geometry and the computational node are Euclidean. So the analysis finish when the non-convergent condition are obtained.
Thanks.
May I ask a question, Mr. Chairman?
I see Sami have a question on the chat. For the mail, what software did you see for this simulation to create this automatic algorithm?
Yes, hello, Mr. Chairman. May I ask this question? It's me who writes it in the chat.
A moment.
Hello?
I don't see the chat.
The question of Sami is, what software did you use in this simulation to create this automatic algorithm? What software?
Okay. We use console to
With the physics.
of the algorithm is written in on MATLAB.
Did you use the algorithm for MATLAB? I didn't hear you quite right.
What? Can you repeat?
You used the software. You said console, and I think I heard you said something that you have the automatic algorithm was writing in MATLAB. Is that right?
Yeah. There is an application with colleague console and MATLAB.
If I can be honest, I found it difficult to find how to write automatic algorithm for my own research. So can you at least indicate me from where did you come to from this from the literature that helped you write this algorithm?
Oh, sorry, I don't understand.
Okay, sorry. Thank you.
Okay, sorry.
Can you repeat slowly, please?
Yeah.
Okay.
Another question, Mr. Chairman, very short. You mentioned that you validated your model against an analytical solution.
Yeah.
Is it true?
Of Murakami.
So, what are the assumptions of this solution? Do they take into account the interaction between crack tip and boundary? Or do they consider an infinite medium?
I don't understand. Can you repeat, please?
The analytical model by Murakami.
Yes.
Does it consider an infinite medium or a medium that is of finite dimensions comparable to the dimension of the crack?
Use the same dimension. We use
I mean, is there an analytic solution for a finite domain with a crack of finite length? Or the medium is considered infinite?
Can you hear me?
Yes, of course.
Yes.
Okay. Can you repeat, please? Sorry.
Murakami's model.
Yeah.
Does it consider a plate of finite dimensions or infinite dimensions?
No, finite dimension.
So there is a closed solution for a finite model.
Murakami infinite dimension.
Infinite.
Yeah.
So there is no interaction between the crack tip and the boundaries of the medium.
Yes.
In your numerical model, however, the plate was of finite dimensions.
In the numerical model, we use the finite dimension.
So how could you compare a solution for infinite medium with a solution for finite medium?
Okay. Because Murakami give a coefficient to correlate the results in infinite plate with finite plate.
So there are correction factors.
Yeah.
Okay, thank you.
Sorry.
It's clear.
Thank you.
Thank you.
Thank you, Domenico.
Thank you.
And the next presentation is on the critical influence of teeny geometrical details on the stress field in a Brazilian disk with a central notch of finite width and length. Authors are Professor Stavros Kourkoudis, Christos Markides, and Hermione Pasio. Please, Professor Kourkoudis, I suppose.
It will be presented by Dr. Pasio.
No, it's me.
Oh, Noni. Good afternoon.
Good afternoon, ladies and gentlemen. The present study is an attempt to quantify the influence of geometrical details on the stress field developed in a Brazilian disk with a central notch of finite width and length. So a centrally cracked circular disk is studied both numerically and analytically, and the crack is considered as a rectangular slit with rounded corners. The parameters studied include the length of the notch, the width of the notch, and the radius of the corners of the notch. The analytic approach solves the problem where the load is parabolically distributed along a finite arc of the disk. The problem is solved in 2 dimensions, employing the Muskelis-Willis complex potential methods. In the beginning, the general solution of the infinite plane, for the infinite plane with nodes is obtained. And afterwards, this solution is combined with the solution for the circular ring, and therefore the circular disk with notches obtained. For the numerical analysis, a 3D model was constructed, keeping the geometry of the disk and the nodes the same as they were considered in the analytic solution. In addition, the loading patterns proposed by the ISRM standard were also taken into account. The numerical model was validated based on the results obtained by the analytic solution, and the validation considered very satisfactory. As a next step, the parametric investigation was carried out, and based on the results obtained, it can be said that the study highlighted the role of the 3rd dimension. Differences approaching even 20% on the stresses developed at the front surface of the disk and at the central cross section were detected. The role of the radius of curvature on the stresses was of minor importance. On the contrary, the width of the notch plays a much more important role on the stresses developed, and the same is true for the length of the notch. Recapitulating, it can be stated that it is very important to take into account the exact geometry of the notch. Otherwise, we may lead to erroneous results concerning the stresses developed, and therefore to misleading results concerning the actual fracture toughness determined for the disk's material. Thank you very much.
Thank you, Noni, for your presentation. Any questions?
If I have the permission, Mr. Chairman, the main idea is that the standard for the determination of fracture toughness in very brittle materials, in fact, is based on a solution which takes into account a mathematical crack. The mathematical solution for the stress intensity factors used by ISRM or ASTM is the solution for the so-called crack straight through Brazilian disk. Because we have no solutions concerning a finite disk with a finite crack. So we tried to highlight the critical role, for example, of the width of the notch, which is ignored by the standard. And as you have seen, it is in fact crucial. So perhaps the standard should be reconsidered on the basis of the actual stress intensity factors, which cannot be determined from the crack straight through model. That is the main idea, and it is supported by the analytical solution, which is very recently published. That is the main idea of this project.
Thank you, Professor Kourkoulis. Very interesting. I have just a curiosity. In the simulation, using the software, finite element software, the generation of the mesh is critical. Is a critical process, or you can choose a coarse mesh, for example, in order to calculate solution very close to the actual solution.
Messing is always crucial. So either in ANSYS or in any other program, software used for finite elements. And this is why before the main study, always the preliminary study is carried out in order to find the optimum size of the elements according to, we basically carry out a convergence analysis. It's always the basic step and the first step. And without this one, we cannot proceed.
Okay.
However, I
Thank
should
you.
highlight that we had some discrepancies. We have to be honest. If the crack is very long, which means that the interaction between the crack and the boundary is very strong, analytical models fail to predict or to give the same results with the numerical analysis. And so there is a problem left to experimental study to see who is finally right. But the mesh obviously plays a crucial role. We hope that the mesh used is ideal for the results to be mesh independent. For moderate crack lengths always.
In the experimental way, it's always not so easy to correctly put the samples in compression tests.
Be patient,
Because,
Mr. Chairman. Tomorrow we have experimental results for the same topic.
Yeah. Thank you, Noni. Thank you, Professor Kourkoulis.
Thank you, Mr. Chairman.
And the next presentation is a computational and experimental study of strain localization processes on the post-critical stage of deformation. Authors are Mikhail Tretyakov and Valerie Wilderman. Please. Mikhail or Valerie? Are you online? No, okay. I suggest to perform the next presentation. Effects of long-term operation on mechanical and physical characteristics of structural materials by Turin, Botwina, and Joffe. Please, Turin.
Hello.
Thank you, please do.
Okay. Hello, everybody. My name is Marat Tutin from Moscow. And I, with my colleagues, Professor Botwina and Dr. Joffe, will present a study on effects of long-term operation on mechanical and physical characteristics of structural materials. We studied two widely used in industry steels. Bayonetic steel is used as a material for all the cycle rods, and we studied in three states: in initial state, after operation, and after hydrogen saturation, by exposure in the NACE environment to enhance the structural degradation effect. Stainless steel we studied in two states: in initial state and after operation as a vacuum chamber body. Operation led to a slight decrease in the strength of the bayonetic steel specimens and to a slight hardening and reduction in ductility of stainless steel specimens. Hydrogen saturation causes a significant decrease in elongation and fracture work of bayonetic steel. Fatigue strengths of bayonetic steel after hydrogen saturation and stainless steel after operation decrease. The impact toughness of the bionic steel specimens after operation practically did not change, but dynamic fracture toughness in the temperature range from the minus 40 to minus 60 C is higher. We associated it with the defects formation during operation, which dissipated energy during impact loading. Four stages of fracture during tension were distinguished, and changes in acoustic emission parameters and magnetic characteristics were analyzed. We can note a decrease in the acoustic emission activity in specimens of bionic steels after operation. The magnetic characteristics change most intensively at two stages, and the initial stage 1 for the yield strengths, and at the final strengths, a final stage 4 before the final fracture. Hydrogen saturation without loading leads to a decrease in the acoustic emission activity. After saturation under load, we observe increase in the acoustic emission activity. Uniform acoustic emission observed at all stages of fracture, which indicates the development of the defects under loading that originated during the hydrogen saturation. A similar trend is observed during test of stainless steel specimens. Operation leads to a decrease in acoustic emission activity. The kinetics of changes in magnetic characteristics in both specimens, in both states, is similar, but the growth of the magnetic parameters is observed at earlier stages of fracture in the specimens after operation. Thank you for your attention.
Thank you very much, Marat. Any questions? No one? Okay, I have a curiosity. Firstly, I think this is a very good work because show us how the material changes the mechanical property after operations and after, for example, exposition to hydrogen. And you, in your work, show us how the material change not only the mechanical property, but also other kind of property as magnetic permeation and other one. My curiosity is how can we correlate the measure of magnetic field on or other properties directly measured on the material to the mechanical properties, degradation after operation or after exposition to the hydrogen environment?
Thank you for the question. In our study, we can note that the most sensitive method to the structural degradation during operation is the acoustic emission. The magnetic methods shows the similar results after and before operation, and this should be studied further because these very complex methods. And we will continue these studies on other materials and on the other operation conditions.
Okay. Thanks for your answer. I see in this slide the acoustic emission. This is the emission measured during the tensile test.
Yes, of course.
Very interesting, because in the elastic field we can see signal very high. It's not noisy. It's a signal. It's evident how works in the elastic field the material in terms of acoustic emission. This is a normal steel. Have you any experience in the other kinds of the alloy, metallic alloy, for example, aluminum or titanium-based alloy?
Yes, of course. We studied the performance tensile test on steel specimens with different structures, on aluminum alloys, and so on. You talk about the high acoustic emission activity at the first stage of fracture, as I understand. Yes.
Yes. Yeah.
Yes.
Seems
this is normal.
Is normal.
Yes,
the acoustic emissions seems to be related to the high values of the stress rate, because in elastic field we have a sloping increase of the stress. Instead, in the plastic region, the signal of the emission seems to be low. And in this case, with the increment of the stress is not so high. Seems to be this is the effect.
We can talk about microplasticity processes and dislocation of movement at this stage, and that cause acoustic emission activity.
But in elastic field, the theory tells us that the dislocation are fixed or almost fixed. Seems to be
there is stress concentration due to structures defects and so on, and the dislocations can be near these defects caused by these defects during tension.
Okay. Thank you, Marat, for your presentation.
Thank you.
And I repeat the call of Mikhail and Valerie. Is there? No. So I introduce the next presentation. The effect of laser cladding on the wear behavior of gray cast iron disc brake by Pietro Tonolini, Lorenzo Montesano, Annalisa Pola, Ettore Landriani, Marcello Gelfi. Please.
Good morning, everyone. Can you hear me?
Hi, Pietro. Please.
So, thank you for the introduction. I'm Pietro Tonolini, PhD student at the University of Brescia, and I'm here to talk to you about the work called the effect of laser cladding on the wear behavior of gray cast iron disc brake. Recent studies have demonstrated that a part of the total non-exhaust particle matter emission produced by a car derives directly from the wear of braking system. Currently, commercial high velocity of the fuel coatings disc brake have been found to be effective in reducing this emission. However, these coatings contain harmful elements or with suspicion of damage to human health more than iron particles, such as nickel and cobalt. In this context, this work aiming on the possibility to replace wear-resistant coating hazardous material for gray cast iron disc brake application by stainless steel powder deposited via laser cladding. In particular, two types of powder was deposited, martensite stainless steel and the same powder reinforced by the addition of 2 second biparticle. Gray cast iron and the coatings wear behavior was evaluated through pin-on disc and block-on-ring test, utilizing commercial low metallic brake pad friction material samples as counterpart. gray cast iron and a commercial like velocity oxy-fuel sample was used for comparison. Furthermore, SEM analysis was employed in order to investigate difference between the worn surface. And the results demonstrate that the proposed laser cladding containing tungsten carbide particle is effective in improving the wear resistance of both the disc and the wear pad, with wear rate slightly higher than those of the high velocity oxy-fuel one, and but without the use of harmful material and with an overall cost saving. The wear behavior of the stainless steel coating is the worst, but further investigation are needed to understand the wear mechanism. So this work demonstrates the possibility of improving the wear resistance of cast iron brake disc by using powder coating of stainless steel with hard particles. This is a good starting point for expanding application of laser cladding, and a new powder composition will be tested in the future. Further investigation and development are needed in order to enhance the laser cladding adhesion to the substrate and to improve the homogeneous dispersion on tungsten carbide particles in the aluminum in the stainless steel matrix. And thank you for the attention.
Thanks to you, Pietro. Any questions? No one? Firstly, a curiosity. The effect of laser cladding in terms of the friction coefficient of the disc brake, which is the effect?
It's a good question, because it's a good question because the pad material used is a commercial brake pad material optimized for the gray cast iron brake disc. So I can share this presentation. Okay. Can you see the coefficient of friction in this slide? For example, this is the pin-on disc test on coated gray cast iron disc, and for sure, the gray cast iron brake disc show.
Pietro.
Yeah.
We are watching the first slides.
Oh, I'm sorry. Okay. Now you can see the coefficient of friction plotted under the sliding distance. And for example, the gray curves show the behavior of the gray cast iron samples. And you can see that the coefficient of friction is very stable under the total sliding distance. This behavior is very similar to the high velocity oxy-fuel one. But this is not true for the true laser cladding. Well, for the laser cladding with the hard particles, the coefficient of friction is similar to that achieved by the gray cast iron, but at the end of the test show uprising. The yellow curves achieve a coefficient of friction higher with respect to the gray cast iron. Differences on the behavior of the stainless steel coatings that experience a very higher coefficient of friction with respect to the other samples. This behavior will be analyzing through different tests and through the further investigation of the worn surface.
I think, but it's only my opinion, that in the orange curve, the coefficient is not so useful because you have big differences between the first part of curve and the last part of curves. In terms of usability on the car or other kind of machine, the brakes is not efficient in this way because you have to hit the devices in order to have a good performances of the brakes.
Yeah, this is true, but ideally, the more the coefficient of friction, the short is the braking distance. So this is a conversely point of view. This behavior can be what I can say, through an initial running stage, for example, we can delete this this behavior at the beginning of the course. But the problem here is the IGF wear rate. As can be see here, the stainless steel coating experience the highest wear rate with respect to the other 3D sample. So the coefficient of friction, I think that is a secondary problem to solve.
This is the wear rate of the disc or of the lining?
Both the disc.
The wear rate, both. Oh,
the wear
pin and disc. Yeah.
Yeah, both the disc and the pin.
The disc is very high.
Yeah.
Okay. And the effect of the laser is reported in the yellow curve.
Yes.
It's correct. It's correct. Okay. It means that for high values of X, we have an increase of the friction coefficient. It means that the shape of the surface changes, or it is an effect of the temperature or other.
No, probably it's due to the wear debris on the one surface that act as a three-body wear mechanism, so enhance the coefficient of friction and reducing the wear resistance of the coatings.
The hazard is that you can have a stop of the brake due to the grip of the lining on the disc. It could be or not.
Can you repeat, please?
Il grippaggio. It's a brake, the stop of the brakes. This is the hazardous, or is not important in this case because the friction is lower than 0.6.
Well, it's hazardous, but at the laboratory scale, I think that there is not the same to evaluate the wear behavior on laboratory scale, and that happens, for example, on a dyno bench test bench. In fact, the possible reduction in the particulate matter production during braking with respect to the standard great cast iron braking system will be evaluated and compared in the future on the dynometer test bench. And so we can compare difference between different tests.
Yeah, you can play changing the shape of the brakes and the lining because it's important.
And the dimension, yeah, of course.
Yeah. Thanks, Pietro. Other questions from the colleagues online? No one? Thanks, Pietro.
Thank you very much.
Thank you to you. I recall again Mikhail Tretikov and Valerie Wildman. Are you online? No? Okay, we can close this section. Thanks for your works and thanks for your presentation. Mainly, firstly, to Jose Antonio Correia for its invited, very interesting invited presentation, and to all presenter. And thank you. See you soon. Bye.
Thank you, Mr. Chairman.
Next session is start on an half past 4 in PM. Okay. This is the communication. Other information? No one? Thank you. Thank you, Professor Kourkoudis.
Bye, Vittorio.
I always
Bye,
love your wallpaper, Mind Warp.
Thank you very
Remember
much.
well.
Goodbye.
Thank you. Bye.
Okay. Good afternoon. Welcome to this fourth session. My name is Andrea Spagnoli. I work at the University of Parma. We have 12 presentations in this session. Okay, I think we can start with the first presentation, which will be given in presence by Patrizia Moccano. And the title is Additive Manufacturing Processes for Metals and Effects of Defects on Mechanical Strength, a Review. So please, Patrizia, the floor is yours. I will move aside.
Okay, I'm going to share my screen. Okay, good afternoon. I'm Larissa Moccano, University of Cassino in Southern Lazio. And in this presentation is a collaboration between us from Cassino and Norwegian University and TNU. The work is a review on additive manufacturing defects and their effect on mechanical behavior, with a brief introduction on the additive manufacturing processes for metals. So first of all, I started with an introduction of the causes of occurrence of defects. So we can have the Kiel mode and the Bolling phenomenon, where we can act on the laser power and the scan speed. So modifying them, we can minimize the defects. And in addition, we can also have the, of course, quality of material feedstock. And then I described in detail the main type of defects. So we can have, for example, the porosity, and in this case, we can have two types of porosity: the Kiel porosity, visible here, that are larger in size and irregular in shape, or we can have metallurgical porosity that are smaller and with regular shape. And similarly, we can have other type of defects. So for example, residual stresses, lack of fusion defects, roughness surface, thermal microcracks, and of course, all of them lower the mechanical resistance. Minimize these defects during the printing process is not that easy, because all the parameters mutually influence each other. And even if we find an optimal set of parameters, this can be applied only on the individual case analyzed, and not to all materials and in all conditions. Another way to minimize the defects is using post-processing treatment, but in this case, of course, this increases the production time and also the production cost. Thank you.
Okay. Thank you. So now the paper is open for discussion. If there are questions from the audience here or online, please. So maybe I can start with a short question regarding, let me see, we were talking about measuring residual stress. Well, you mentioned residual stress as a source of possible influence on the strength. Did you measure experimentally the residual stress in your specimens?
I analyzed all of these defects, and I described their effect on mechanical behavior and how they occurred during the printing process. So for residual stresses, the residual stresses act as a zone where the stress applied is amplified, and of course lowered the mechanical resistance of the material.
Maybe it's useful for the benefit of the audience. Maybe you can tell us something regarding the printing parameters that you can control in this manufacturing
we can control
process.
the scan speed and the laser power, that are the main two process parameters, because they are responsible for these two physics phenomenon, Kiel mode and the Bolling phenomenon. For example, in the Kiel mode, we can act on the laser power, because, for example, in this case, we have a higher laser power, and of course the Kiel mode is amplified. And for example, in this case, we have a lower laser power, so we can have better conditions for the material.
And regarding the fatigue strength, in your opinion, what is the key feature that mostly influence the strength? I mean, is it more relevant the porosity or the surface roughness in terms of fatigue strength?
Yes, the roughness surface is more important, according to me, because the surface is, if is not polished, act as a lot of zone where the stress applied is amplified, so we have a lower fatigue resistance.
Thanks. Maybe there is any other question or comments, please. And well, maybe I can ask you regarding the printing time. I mean, did you follow the additive manufacturing process of these specimens in your work?
No, this is only a review, so I analyzed only this part of the topic.
Mm-hmm. Okay.
So I didn't do physically the printing process.
Okay. And you were concentrating on which technique for printing? I mean, from my understanding, you were studying 3D printing of metallic materials.
Yes, yes. For example,
using
PBF or TID. In this case, these are PBF components. In this case, and in this other case, PBF components. So the quality of powder feedstock is important.
Okay. So if there are no questions from the audience, I think we thank again Patricia.
Thank you.
And we can move to the next presentation. Thank you again for your interesting review. I think now we can move to the second presentation. The title is Numerical Modeling of Mechanical Response of Lattice Structures Produced through Additive Manufacturing, and will be presented again in presence by Andrea Tridello. Please. Do you know how to...
Okay, please.
This presentation, this work deals with the analysis of the experimental and the numerical behavior of lattice structure produced through additive manufacturing. This work has been done with the Society Altair. The main objective of the project is the design of a crash box made of lattice structure to increase the energy absorption. In this presentation, in this preliminary activity, I will focus on the assessment of the cell, ensuring the highest absorbing capabilities, and on the simulation of the compressive behavior of this lattice structure. For the assess the cell with the highest absorbing capabilities has been assessed through experimental compression test on 5 lattice cells with different geometries which were available in the literature. The specimens were produced in carbon nylon with the geometry reported in the slides. And by comparing the energy absorbed, the peak force, and the specific energy absorbed, the cell with the highest absorbing capabilities has been defined and used for the following activities. The geometry is reported in this slide. Thereafter, a model of the specimen used for the compressive test, for the compression test, was created by using 1D element in order to reduce the simulation time and to obtain the reliable results. The model was found to be in agreement with the experimental data, as can be seen in this slide, and also the displacement, the failure mode was found to be in agreement with that found experimentally, as can be seen. Thereafter, the same tests were repeated on a specimen, on the same specimen with the cell defined previously in aluminum silicon tag magnesium alloy, which is the material that probably will be used for the crash box. Even in this case, the model was found to be in agreement with the experimental data, but we don't use the model that we define for the carbon nylon, but we have to insert a failure mode in order to properly model and the failure behavior of this material, because there is an interaction between the cell stiffness and the failure mode. So the main conclusion of this preliminary work are we were able to determine, to assess the cell ensuring the highest absorbing capabilities, and we did it experimentally and non-numerically, as generally done in the literature. And the experimental behavior of lattice structure can be simulated with 1D beam elements in order to reduce the testing time, but it is important to take into account the interaction between the cell stiffness and the failure mode in order to properly compare, in order to properly assess the cell behavior. So thank you very much for your attention, and I'm available for questions.
Okay, thank you, Andrea. So now we have time for questions. If there is any question from the audience here or online, please. Okay, otherwise I can ask you maybe some details on the numerical simulation. I mean, did you process of response of the lattice structures even in the final densification stage, or and in this stage I guess you somehow simulate the contact between the elements?
We did not model the last part, the densification, because it is not of interest in for crash box. But we had to insert a contact which was available in the software to model the failure modes, the layer failure, which are these peaks and valley, Otherwise, we will not able to simulate this behavior. For the aluminum alloy, on the other end, we found a different failure mode, 55°, and so we had to introduce the failure mode to model this different behavior after the peak force. So, but the objective is to obtain the results in a limited testing time in order to design the crash box, but starting from a model which is validated, because in the literature, in general, a single cell is modeled with 3D elements, and then this behavior is considered for the design, but in general without any experimental validation, which we think is very important. But it is also important to obtain the results in less than 80 hours that we found for a 3D model, complete spacing.
But when you're talking about failure mode, I mean, did you consider in your simulation a failure criterion of the material itself, of a materials composing the strut?
Yes, we insert a maximum
stress
deformation.
Maximum deformation.
At which the element is deleted. For example, otherwise we were not able to model this decrease, and we obtained the same behavior. It was important to test the two materials because it points out that you cannot transfer a model from a cell to another, because we think the cell stiffness is important in assessing the behavior. And this is for static loads.
I was going to ask you, did you consider quasi-static test?
Yes. The next step of this project is
to consider rate dependent.
Yes, and we will start with some experimental tests, but we have to work on simulation because it's not so. So the model seems to work, but we have to find the strain rate effect and the parameters to consider in the model.
And what about boundary conditions on the sides of the specimen? Did you consider some kind of periodic boundary conditions, or
no?
I mean, I'm talking about this.
No, we only consider.
They are free to display.
We tried in different ways, but this one was most close to the experimental results.
Okay. And I mean, from my understanding, the key parameter that you are looking for is the energy absorbed for unit volume or unit mass.
Yes.
What about this system, the performance of this system in comparison to other absorbing materials like foam, polyurethane foams?
We did not check it, but we started with carbon nylon because we had this 3D printer in the lab, and it is easy to print this material and also cheaper to. And then with aluminium, but we found that with this configuration, the aluminium alloy is not so good. We didn't think so. But on the contrary, carbon nylon has a very good absorption capabilities and not high peak force, which is not good for crash box. So we are also thinking about using, for example, plastic materials or material reinforced in place of aluminum alloy, which is also more expensive. And also it weighs more.
What about the applications that you have in mind?
The application is a crash box for automotive application to absorb low energy impacts. So because we have also the possibility to use a drop dart testing machine, and this is the possible application for higher energy impact. I don't know if it is suitable for this application.
Okay. Okay. Thank you, Andrea, for your speech and for answering questions. So I think now is my turn, actually. So I'm going to switch from chairman to presenter very briefly. Let me get my presentation. What is it? Okay, so this is the title of my work, Fracture of Polymeric Materials, Linking Continuum and Molecular Models. Just a second, but we have a technical problem. Quindi non lo stavo condividendo prima. Non mi avete dato istruzioni. Quindi la presentazione precedente non era condiviso. Vediamo. Ah, quello qua, no. Devi ingrandirla e poi devi condividere. Ah, ok. Tutto lo schermo. Ok. Ma condivido le finestre o tutto lo schermo? Lo trovi facile. E la presentazione è questa qui. Ok, ok. Okay, so apologizes. I think that we had a problem even in the previous presentation and from remote connection, you are not able to see my presentation and also the previous one. So I'm sorry for that. So you are only listening to the audio, but not video. I'm sorry. So I think now should be okay. Okay, so the title is Fracture of Polymeric Materials, Linking Continuum and Molecular Models. I'd like to acknowledge my co-authors, my colleague Roberto Brighenti, Michele Terzano, who is a former PhD student at the University of Parma, now is a postdoc at the Graz University of Technology, involved in biomechanics problem, and Mattia Cosma, who is currently a PhD student at Parma University. So as you can see from the title, we are talking about polymeric materials, but in general, we are dealing with soft materials. And in particular, we were focusing on the failure of these materials. And as you know, soft materials are undergoing very large deformation, so all the framework of in the continuum mechanics involves finite strain, and they have very peculiar features, which include a very high toughness. So in this work, to give you just a couple of highlights, we were looking at the stress fields in the vicinity of cracks. And when you are dealing with soft materials which can be modeled with hyperelastic models in the continuum framework, you notice that you have singular stress fields which are much different from those that are well known for linear elastic fracture mechanics. And also we have the development of blunting of a crack tip. So all these aspects are very relevant when you look at the toughness of the material. So we were investigating these aspects from the continuum mechanics point of view, but also we try to give some insight considering some micromechanical models where we actually we were actually simulating the behavior of polymeric chains. And so all these aspects involved some concept related to entropic elasticity and so on. one of the motivation of the work is listed here. There are many motivations, but most of them here are concerning with biomechanical applications and are related to the mechanics of soft biotissues. And these are very important. Understanding is very important when we are dealing with problems where there is an interaction of biotissue with some for instance, tools related to micro surgical procedures or in other applications related to, in general speaking, to puncturing or penetration of soft tissues. In all these aspects, it's very important to understand the fracture and the failure process of the soft material. So to make it sure, I just want to pick up this slide where you can see the near tip stress field, considering an hyperelastic material, neo-Hookean material, but also there are other generalized neo-Hookean material where a parameter of strain hardening is varied. What you can see is that the singularity of the stress field is different from the square root of R, and also the singularity is different depending on the stress component that I'm considering. Another aspect that we investigated is the region where this singular stress field are relevant, and of course, because we are dealing with nonlinear elasticity, this regions depends on the applied remote stretch, which is this lambda parameter. And these are some pictures related to the elastic blunting, which can be very much varied depending on the on this parameter of the hyperelastic generalized neo-Hookean model. And finally, this is just a slide. Of course, there's no time, but I hope that you have followed the video, and I'm here also to answer your questions. This is just a slide to give you just a picture of the micromechanical model which deals with the mechanics of the polymeric network. Okay, I think I've said more than enough. Well, this is a picture showing the stress distribution obtained with a micromechanical model. And so the attempt was in this work was to to find some correlation between the continuum mechanic approach and the micromechanical approach based on the mechanics of the polymeric network. So thank you. I'm ready to answer your questions if there is any. I cannot, of course, make question to myself, so please. Yes. Yes. Scale approach, and the second question is that I see that the focus on the stress field, let's say, so I wonder if you have some ideas about how to make
choose stress intensity of the rest.
Okay, thank you, Pietro, for your questions. Okay, regarding the first question, which is related to the multi-scale feature, what we have done up to now is to try to make in two steps the multi-scale approach, in the sense that we are dealing with a specific geometry, which is that of a pure shear testing, which is, I don't have a slide here, but is a common test that is used for rubber-like material, where you have a stripe of material, a long crack, and you apply a stretch, remote stretch. So we run a very refined finite element analysis using hyperelastic material, and in this way we were able to obtain the displacement field to be applied in a region close to the crack tip. On that region, we then run the micromechanical model, which have rather complex formulations, but and is for some aspect is very time computationally time consuming. And because we don't have any dissipation source in the micromechanical model, we can progressively apply the displacement along this circular path and follow the response obtained from the micromechanical model. And the other point was regarding, yes, the criterion for crack propagations. This is a very good question, and in fact, for rubber-like material, the standard in the literature, there are old works from Rivling or others, which were dealing with rubber materials, were all of them based on energetic approaches. So they were calculating the tearing resistance of the material and having yes, energetic critical terms for crack propagation. If you are trying to use a stress-based criterion like a K, stress intensity factor, for this nonlinear elasticity, it gets into trouble. So maybe a single parameter from our experience is not enough to have a crack propagation criterion. Okay, so if there is any other questions also from online audience, please. Otherwise, we move to the next presentation, which is entitled Computational Mechanical Modeling of the Human Skin for the Simulation of Reconstructive Surgery Procedures, and will be given by Riccardo Alberini. Please, he will give his speech in presence. Okay, thank you. Please, Riccardo.
Thank you. Good evening, everyone. My name is Riccardo, and I'm going to talk about computational mechanical modeling of human skin for simulation of reconstructive surgery procedures. So there are several types of surgery procedure on skin. First, to correct the anintropion of the lower eyelid, and then to elongate a scar after a contraction. So The technique is widely used in surgeries, but it is not well understood the mechanical behavior. So we decided to simulate the process into a finite element framework. And so the material, of course, is hyperelastic. So we use the non-dense strain energy density function to simulate the constituted model. The membrane is computed under incompressible and plane stress condition. And of course, skin is also under initial deformation state. So we added an initial stress state to the model. There are difficulties in generating the model, so we decided to generate an algorithm to create the models. And so the algorithm first takes as input the geometry. Then for the closure, it generates nodes along the inner boundary. And then finally, it generates the mesh, refining the element size around the discontinuities in the inner boundary. So this is the analysis. The analysis is performed in the Abacus environment. So this is an example of the Z-plasty during the transposition of flaps. And as you can see, the closure is perfect because we used multi-point constraint around the inner boundary to get the perfect closure. So the algorithm has been used to optimize the Z-plasty geometry, and we decided to analyze a 36 combination. And the parameter used is an efficiency parameter, which maximizes the elongation effects of the surgeries, and also lowers the side effects due to the low angles and the high deformation around the inner boundary. So this elongation efficiency generates an optimal configuration of 60 degrees angles between the limbs of the Z-plasty. So the algorithm, of course, is capable to generate different geometries and different surgeries. And in fact, we decided to try different geometries, including the multiple Z-plasty, the W-plasty, square flap, and four flap plasty, achieving good result and using the same base algorithm to generate the models. Model using the hyperelastic model, including all the non-linearities of material and geometrical. The 60 degrees Z-plasty is confirmed as the optimal configuration. And the algorithm is capable to generate topologically complex geometries. So in future, we are planning to generate a wrinkle model to code the no compression of the material, and also validate our models through testing in vitro on phantom tissue development obtained through additive manufacturing. Thank you for your attention.
Okay. Thank you, Riccardo. So if there is any question, Alberto.
Yes. It is just an assumption. The main effect we want to maximize is the elongation of the Z-plasty. Of course, not the configuration has some drawbacks because high tension in the tissue generates necrosis. So we used a penalty factor, which is the deformation, the high effective deformation. We also include the low angle of the flap because low angle flap have a short basis of the flap connected to the other skin, which reduces the blood flow in the flap. So we use these parameters, but we can find different parameters to generate the efficiency, to calculate the efficiency. It is just an assumption. Yes.
Okay, I think, well, we are on time, but if there is any other questions, maybe we have still a couple of minutes.
We demonstrated that they already use the 6060 blast is the best. Of course, surgeons don't know why, but we confirm that is the best choice. Empirical, because it is a surgery developed about 150 years ago. So it works, and but they don't know why. So we try to demonstrate the effective configuration is the best.
Maybe if I can add, as I'm one of the co-authors, this shape, Z shape, is such that the two triangular flaps are rotating, so the kinematics is a bit funny, peculiar, but is made in such a way that you rearrange the stress in the surrounding region. You can see here. Okay, thanks, Riccardo.
Thank you.
So now is the turn of Professor Sapora. Alberto is going to talk about comparison between two non-local criteria, a case study on pressurized holes. Please, someone. Okay.
Okay, so thank you, Mr. Chairman. Well, I would like to thank Professor Cornetti from Polytechnic di Torino and Professor Efremidis from the University of Thessaly for this work. So basically in this work we have compared two non-local criteria, while the first one is gradient elasticity, so it results non-local in the elastic constitutive law, but basically is local in the failure criterion since it's related to the stress concentration factor. On the other hand, the second criterion is fine fracture mechanics, which actually is local in the constitutive law, but not local in the failure criterion since it's based on two conditions, one stress and the other energy, just one stress and energy conditions, which have to be simultaneously fulfilled. So in order to compare the two approaches, we have considered these geometries. So we have a circular hole in an infinite plate. The hole is subjected to internal pressure, both to internal pressure and far field tensile loading. So that's the situation before and after basically crack propagation. So just a few words on the gradient elasticity. So the constitutive equations are based basically, so it's based on local constitutive equations, but the kinematic and static equations keep the same. So after some analytical manipulations here, I skip, basically we are able to obtain the up stress, sorry. So we are able to obtain the up stress, which varies basically as a function of the hole radius. And of course, so since the stress field varies, so we can assume as a failure condition this one. So failure happens when the maximum up stress reaches the material tensile strength. On the other hand, the second approach is fine fracture mechanics. So it's based on two conditions. The former is an average stress condition. The second is the energy balance. thanks to Irwin's relationship, we can express the energy balance in terms of the stress intensity factor function and of its critical value, which is namely the material fracture toughness. So in order to implement FFM, we need the stress field and the stress intensity factor functions. The stress field is known by Kirsch's solution more than 1 century ago. On the other hand, the stress intensity factor function can be found tabulated in the stress intensity factor handbooks. And just to say something, that both criteria are based on material length. So in order to compare the predictions by the two criteria, we suppose a proportionality, a proportional relationship between this inner length. And then, of course, this proportional coefficient beta basically was fitted. And then we compared the predictions for the case of biaxial loading, so no internal pressure in this case. Then we compare the predictions for just internal pressure, so in this case, no far field loading. And as you can see, that the matching is good, at least for over the range of practical interest. And we compare also prediction with experimental data. In this case, they refer to rock materials. And finally, we compare the predictions for the case of combined loading sigma plus P. And these are the conclusions of my work.
Okay, thank you. So there are questions here in the audience or online, please. Otherwise, I might ask you a short question. Thank you for your, first of all, for your work and interesting work. You were showing a parameter beta correlating the two length, characteristic length.
Yeah.
Did you choose or do you have a criterion for choosing this parameter, beta, which is a factor?
Well, it's a scalar basically. So we chose it for best fitting. I mean, in order for the prediction by the two criteria to be as close as possible. So, but the interesting thing, at least according to me, in this work is that, both criteria are based on a critical length. Gradient elasticity is based on this length, which is generally fitted on the experimental data. So it's an internal length, which is related to the microstructure of the material, but generally from a practical point of view, it's fitted basically on the experimental data. On the other hand, as concerns fine fraction mechanics, the distance is basically a function of both the geometry and the material properties. So K1C, the fracture toughness, and the tensile strength. So of course, maybe there are some problems to evaluate the fracture toughness or the material tensile strength, but if you have them, basically you have the critical crack advance. So by supposing a proportionality law as a proportional law as in this case, we are able also to estimate the critical length for gradient elasticity starting from K1C and sigma C. So.
And one of the graphs that you showed regarding gradient elasticity, if I understood well, is showing actually the size effect.
Yeah.
Meaning that as the...
This one?
For instance, this one.
This is
showing that as the radius varies, increases with respect to the inner length,
yes,
you have a different failure stress.
Yes. So probably the previous one, this one.
Or this one.
So this is the hoop stress as a function of the dimensionless radial coordinate according to gradient elasticity. According to gradient elasticity, basically the stress field varies as the size of the hole varies. So of course, depending on the size of the hole, you have a different stress concentration factor. And so, of course, in order to impose a failure condition, we can basically consider what happens at the whole edge, differently from classical linear elasticity, where the stress field basically is.
maybe one final question. In your problem, you were actually dealing with an axisymmetric problem.
Yeah, sure.
Or are you planning to try to consider different biaxial stress ratios?
With finite fraction mechanics or with gradient elasticity? Because of course, with finite fraction mechanics for sure. With gradient elasticity, we don't know because it's much more complicated, at least to get an analytical solution, as in this case. Because in this case, thanks to axial symmetry, of course, we are able to. This assumption simplifies, of course, our analysis.
Okay. Running. Okay. Thank you, Albert, again.
Thank you very much.
So we go to the sixth presentation of this afternoon, and will be given by, I think, Dario Milone, or the title is Finite Element Analysis of OT Bridge Fixed Prothesis System.
I have some problem, but
Hello?
I can use my presentation.
No, we can't hear you. Yes, just a second, but I have to. Okay.
Okay. It's right.
Right. Yes.
Okay.
Yes.
Thank you for letting me introduce my work, and special thanks goes to people who work with me to produce this work, that are Dario Santonocito, Giovanni Sidano, Fabiana Ricita, and Gabriele Cerrino. The aim of the work was to define the behavior of anti-bridge fixed prosthesis and highlight the possibility of error of the.
Sorry, Dario, we can't hear you very well.
Okay. May I start?
Yes, please.
Okay. The aim of the work was to define the behavior of OT-bridge fixed prosthesis system and highlight a possible error, the inadequate use of the input, and ascertain the readily effective of the figurine. But what is the OT-bridge system? What I can speak that is system consists by 4 connection screws, and the entire one are inclined by 30 degrees with respect to the posterior one. And inside the abutment, we can there is a dedicated groove that spins a ring, a racing ring that is a figure. We can say that in this work, that the conclusion of this work, we test 4 type of connection. The differences are the number of screws used on the implant, and the conclusions are that it's important to define a correct custom criteria of the bridge prosthesis system in terms of stability. We can say that in the first 2 tests, that the first 2 configurations where was connected the 2 connection screws are better than the other, and we can know that the tests were not use the connection screw is not so good for the stability. The presence of the figure is granted the stability and retention of full arc prosthesis system connection. Thank you for your attention.
Okay, thank you. So if there is any question from the audience regarding this work on biomedical application.
The biomedical application.
So maybe I can ask you a couple of questions regarding the modeling. that you have performed. Did you run linear analysis, or did you consider some non-linear behavior of the materials or other source of non-linearity in your model?
Okay, we consider a different type of contact between all parts of the prosthesis. For example, on the side with the fixer and the abutment, and we use the friction coefficient as a literature, but it's an analysis when we use the masticatory load from the literature. And for example, I can ask you what type of connection we use. We use a friction connection between the parts of the prosthesis. For example, fixer and equator, equator and trigger, and equator and abutment. And particularity is that we use we model the bone as a cylindrical volume, and in this case, but we consider we consider a contact as bonded. The system that we considered is the condition that considered was the perfect integration of the system. And then for this reason, the contact with prosthesis and bond was considered as bonded.
It's a shame that we can't hear you very well, so maybe we, I don't know,
excuse me.
at least here in the room. So maybe we didn't appreciate all your work. It's a pity. But anyway, regarding the results that you are looking for, I noticed that you were looking at the stress in the elements of your implant system. But did you look also at the displacement that the structural element undergo? I mean, did you have any limitation to fulfill in terms of displacement that
we consider the static criteria to evaluate all different analysis, and the stepping criteria was the displacement along the z-axis measured in the height of the figure, because if the displacement was measured in the height of the figure, the prosthesis disease, and that is the worst condition of the system. And this is the point that we consider for the different type of analysis, where for these four analyses, when the changing is defined by the number of screw connected.
Okay. Okay. And regarding the applied load, did you applied load coming from the mastication process, I guess?
Yes. Yes, coming from the literature.
But
they will, okay.
My question is, how do you have made, I mean, I guess there are in the literature load paths available to simulate mastications. But maybe if you can tell us something regarding the mastication load that you apply to your prosthesis system.
That's okay. We applied the load on the two molar, as you can see in the literature. The value of load is 400 Newton for molar. I can see, you can see that we didn't do experimental analysis to calculate the exact load on that processes, but we use the literature as a support of our study.
Okay. Okay. Thank you, Dario, for your answers and for your presentation. I think now it's we can move to the next work, which is entitled Numeric Analysis by XFEM of Hybrid T-Pil Joints. And I guess is going to be given by Riccardo Roca.
Hello, everyone. I am Raul Campilho, a colleague of Ricardo Rocha.
Okay.
Let me share the screen. So the title of this presentation is Numerical Analysis by the Extended Finite Element Method of Hybrid T-Pil Joints. The main author of this work is my former student, Rogério Faria. I am one of the supervisors of the master student work in ISEP, School of Engineering in Porto. The main objective of this work was to apply the extended finite element method to assess the strength of hybrid joints. And when I say hybrid, I mean a combination between adhesive and welding and spot welding, and also perform the comparison with a purely welded joint and a purely adhesively bonded joint. We want to do the strength prediction, the experimental validation of the XFEM technique, and evaluate different criteria for damage initiation and damage propagation. We can see the geometry of the joint. It is a double L joint, which consists of two L-shaped parts connected either by adhesive, a spot weld, or a combination of both to produce the hybrid joint. We can see in the graphic the comparison, the experimental comparison of strength between the different configurations. And from the left to right, we have the first one in gray, the welded joint, with an average strength of approximately 3,500 Newton. We can see the smaller columns which correspond to the bonded joints. So if we compare the bonded joints with the welded joint, we have a reduction of strength. And this reduction of strength was about between 60 and 70%, depending on the adhesive. The Heraldite AV138 is a very brittle adhesive. The 2015 is an adhesive which has some degree of ductility. And the Sika Force 7752 is a highly ductile adhesive, although less strong. And the three bars with the biggest dimensions, they are the hybrid joints. So we have the best experimental result for the hybrid joints for the three adhesives. And between the three adhesives considered in this work, the ductile 7752 from Sika Force is the strongest one in terms of the T-joint. Comparing to the welded joint, we have strength improvements that range between about 37% for the AV138 up to 43.8% for the 7752. So this means that we have a big advantage in considering the hybrid joining technique compared to the purely welded joint with a spot weld between the two plates. The numerical part of this work, which is the main part of this project, consisted of using the extended finite element modeling technique to model the T-joints. We consider the three-dimensional numerical models to account for the circular geometry of the spot weld, but we consider the symmetry conditions to model only 1/4 of the plate, as you can see in the left figure. The elements were modeled as solid, and XFEM formulation available in Abacus was considered to simulate mixed mode damage and crack propagation, and different criteria were tested for damage initiation, namely 3 criteria related to stresses and another 3 criteria related to strains. And we also consider different propagation laws. In the graphic, we can see the comparison for an example joint of the different ones that were tested. In this case, for the bonded joints with the heralded AV138. And we can see that the results highly vary depending on the damage initiation criteria. As a general remark between all conditions, the quadratic stress and the maximum stress criteria, which are denoted as quads and max, were the criteria that allowed better results. On the other hand, the criteria based on strains, they presented less accurate results, since the damage initiation of this type of joints is ruled by stresses instead of strains. So, as a main conclusion, it was shown that the extended finite element method showed to be an accurate tool to model and to strength predict the behavior of the hybrid joints with multi-materials. But we need to carefully assess the use of the damage initiation criterion and the damage growth criterion so that we have good results. So this concludes my short presentation. I am available for questions and I'm happy to answer them. Thank you.
Okay, thank you, Raul. So if there is any question from the online audience or in presence, please. Otherwise, I can ask a short question. When you are, like in this slide, you are talking about crack propagation. Do you mean that you implement in your model a cohesive crack model or something like that? How do you simulate the crack propagation in your model?
Yes, in these models, we are using the XFEM. And we have, similarly to cohesive zone models, after reaching the damage initiation criterion, we have different laws to access the separation between the crack faces. In this work, I tested both the triangular and the exponential damage models. The difference to CZM, for example, is that in CZM, we need to place special elements in the regions to have crack growth, while the XFEM algorithm, it allows to have a crack growth in regular solid elements from Abacus, but that are whose displacements are enriched so that we can simulate the separation between one cracked element, let's say like this.
Okay. Another question maybe is regarding the 3D modeling. I mean, maybe you can explain us why you decided to perform a 3D model instead of a two-dimensional model. Is it because of a hole in the? I mean,
yes.
Because from my understanding, it seems that the problem can be treated as a plane problem.
Yes, so let me please.
But maybe there is some reason for having a three-dimensional effect.
Yes, the main reason is that we have. Let me just. The main reason is that we have the region of the weld nugget, which is a circular region, and so that we can model this circular spot weld point. We need to use 3D modeling. This is the main reason, so that we don't have a constant shape along the width of the specimen.
Okay. Okay. Yeah. And regarding, I mean, you will show some results, experimental and numerical results regarding the peak load of the adhesive joint. But did you look at also at other parameters like energy needed to peel the adhesive joint or I don't know, other parameters?
Yes, we did. I didn't show in the short presentation, but another study that we considered, this is the full presentation that is available in YouTube. We considered the dissipated energy at failure measured by the area below the low displacement curve. Here we have an example of results. The first column in blue, it's the experimental energy with the standard deviation. But for example, in this graph, I am using always the same criteria for damage initiation, the quad S, the quadratic stress criterion, but I am comparing different power laws, different criteria for damage propagation. And we can see the comparison between the numerical energy at failure and the experimental one. Typically in the experiments, we always had a little bit more energy, maybe due to some effects related to testing machine relaxation and other experimental issues.
Okay. So thank you, Raul, for your time and for your work.
I have a question, Mr. Chairman.
Yes, maybe yes. You have 2 minutes, please.
I have one small question.
Yes.
Thank you. When you have made your simulation, you have simulated only a half of this of your problem. Even if you in the first diapositive, there is two halves, and one of them is how to say it in English. It's closed. It's not maintained for displacement. So why only half?
Well, I consider the symmetry condition.
There is a symmetry. Yeah.
It's this image, right? I consider the symmetry to reduce the computational load, and I considered only 1/4 of the geometry. So I consider regarding the T-joint, I cut it longitudinally and also transversely, applying the respective boundary conditions. We can see here the transversal longitudinal condition.
Thank you.
Yeah, okay. And we clamped the other symmetry face.
Thank you.
Thank you.
Okay, so thank you again.
Okay, thank you.
We now move to the next presentation. The title is Evaluation of Driving Mode Progression Coupled with Overload Effect. And I guess it will be presented by Mrs. Boljanovic. Or maybe Andrea Carpinteri. Is there any one of the authors present online? Can I check? No, I think none of them are present. Okay, it's understandable. Okay, we can, what shall we do? Shall we move on to the next one? Okay. Okay, so we go to the following work. Title is Fracture Parameters of Alkali Activated Aluminosilicate Composites with Ceramic Precursor Durability Aspects. There is a long list of authors here. I don't know if any of them is present on Zoom. Anna Simonova, Martin Lipovtsan, Eva Rotsipalova. Raul, could you please switch off your video because you are still online? Thank you. No, I think none of them are present. So if this is the case, I'll go ahead. Okay, so following work is structural optimization of composite steel trussed concrete beams. And maybe the work will be delivered by Mariangela Deligia.
Yes, and here
okay. Yes.
I try to share my screen.
Good.
Can you see it?
Yes, yes, go ahead.
Okay, hi everybody. I'm Mariangela Deligia. I'm a PhD student at the University of Cagliari. My work deals with the structural optimization of composite steel truss concrete beams. Composite steel truss concrete beams consist in a prefabricated steel truss embedded in a concrete core directly cast in situ. The truss is typically composed of a bottom steel plate. Of a bottom steel plate and a system of diagonal bars and some coupled rebars acting as upper cord. It's important to underline that two constructive phases before and after the maturation of the concrete characterize the mechanical response of the beam, and the two phases differ because of the static behavior, the cross-section, and the applied loads. Optimizing geometry is important because it leads to the minimization of material use, the achievement of sustainability targets, the reduction of the self-weight, and also many architectural advantages. And at this purpose, I proposed an algorithm for the optimization of this type of beams. We can say that the algorithm uses the GA solver in MATLAB to minimize the weight of the beam. And it's characterized also of some nested functions able to perform the calculation of the beam during the first and the second constructive phases that I mentioned before. After I proposed an example of application of the algorithm that I proposed to the homogenized beam that we can see in the picture, the example tried to minimize the volume of the beam, and but only one optimization parameters is considered, which is the height reduction at the midspan that I called delta H, and is subjected to a series of constraint functions that concern the maximum stresses and the vertical displacement at the midspan. Finally, I show some results. I show the optimal geometry that the algorithm found, and also a comparison between the volume after and before the optimization process. I finish my short review.
Thank you. If there is any question from
I have
audience.
a question. Hello.
Yes. Hello, please go ahead.
Yes, thank you. Hi, Mariangela. Compliment for your presentation. You there, if I correctly understand, you there about the structural optimization of this kind of beams. I would like to ask you if do you think to possible application of your method to other kind of beam? And I understand this. I understand that you use your algorithm to reduce the volume of the beam. So my question in particular is if you can apply this criteria to the different material of the beams. So possible development and what is the key to use the optimization with different material?
Okay, thank you for asking your question. Okay, let's say about the future development. I can say that, as I said, now maybe in the main presentation, this is a preliminary study where I proposed the first part of my of the optimization algorithm that I'm studying, and within the example, as I said, I'm considering only one optimization parameter, delta H, which concerns the height reduction at the midspan. But as a future development of the code, I think that I'm going to add some complexities, and I'm going to do that by considering other optimization parameters. Like, for example, we can consider the web bars diameters, also the distance of the between the diagonal bars, but also the height at the extremities, the width of the section or the thickness of the plate. So I'm already thinking about adding complexity and considering these other optimization parameters into the algorithm. I'm working step by step, so I'm building the algorithm. Firstly, considering a very simple problem. In fact, the example is applied to a homogenized beam. This is not a composite steel truss concrete beam, but it's an homogenized beam. So there is no, it is not considered the distinction between the first and the second phase yet. But it was useful for me to apply firstly the algorithm to this simple case in order to understand if the algorithm is working and how it's working. Another possible future development, I think it could be interesting to make a comparison between optimized constant section beam and optimized variable section beams. So, for example, I can apply the algorithm that I'm proposing to a composite steel truss concrete beam with the constant section and with variable section. In order, I think it could be useful to understand which are the advantages, so also the necessity to study variable section beams. So I want to make this in the conclusions. I said that I want to apply this algorithm to a wide range of possible design solutions. And the idea is to use the results of these applications maybe to create tables to support the design of this type of beams. I think it can be used, it can be interesting, and I hope it's interesting from especially from a practical point of view.
Okay.
This is about the future developments. Here you were talking about the two materials. Yes, this beam is made, as I said in the first slide, by two materials, so yes, concrete and the steel truss. And the algorithm tried to, the innovative aspect of this, I think, of this method that I'm proposing is that the algorithm tried to aspire to optimize both phases through the fulfillment of specific constraint functions that are written specifically for phase 1 and phase 2. So there are some design criteria to be respected. So both materials are considered. The total volume is, we have to think about the total volume as the volume of the truss, so the steel, plus the volume of the concrete. And so I was talking about minimize the weight. We consider the volume of the two materials and we multiply them for the weight of the, respectively, for the weight of concrete and the steel.
Okay.
I don't know if I answered to your question.
Yes, yes, okay. It's an interesting topic. I think you can think in the next step, you can introduce also the cost to get to weight and to volume, but it's a good work, compliment.
Thank you. Yes, I already thought also to make the optimization in terms of costs. It could be interesting as well, of course, by considering two different costs per cubic meters for the concrete and for the steel. Yes, I was thinking also as about that as a future development. Thank you. Thank you for your question.
Thank you very much.
You're welcome.
Okay, thank you. Thank you. So maybe I'll just make a short question. You were mentioning that you used in your optimization simulation the results from CalFEM.
Yes.
Correct, for running the finite element simulation.
Yes.
But in your my question is, when you are considering the case study of an arch, which has only a single phase, no? Did you how did you model this arch? Because from my understanding, you were running the optimization in well, in terms of the objective function is related to the volume of the structure, right?
Okay. Yes, the example concern
And did you have any constraint in your optimization process? I mean, like in terms of maximum stress in the structure or something like that?
Yes, are you talking about the example, the case study here? Or you are talking about the trust? Because I used the CalFEM to, I showed this trust, but it's just to see a picture. It's this is not an optimized beam. But you mentioned the CalFEM. As I explained in the presentation, in the main video that I sent you, the CalFEM concern only the first phase. So the first phase is before the maturation of the concrete, where only the steel truss is resisting. So the CalFEM is applied only to the steel truss, because in this phase the concrete is still not mature. It's fresh concrete. So the cross section is given only by the steel truss, and I'm applying the CalFEM to solve the steel truss. This is for the first phase. I applied the CalFEM only to solve the truss during the first phase. While the second phase, I applied the elastic line to the variable section beam. So the application of the elastic line results in a boundary value problem, and then yes, as you were saying, in the example, I considered as constraint functions. The constraint functions concern the maximum stresses and the maximum vertical displacements at the midspan. This is in the example. I consider these constraint functions. Yes, I hope I answered your question.
Yes. Okay. Yes.
Thank you. Thank you for your question.
Thank you. Thank you very much. And so if there are no other questions, we move to the next presentation. The title is Mixed Finite Element for Kinking Track Analysis in an Orthotropic Media.
Yes, hello.
Mr. Sami, yes, please.
Yes, I am Mr. Sami Derwish Sami. I am a PhD student at the University of Skikda in Algeria. This work is being presented with my supervisor and Mr. Bouzer. Dr. Professor.
We can't, sorry, we can't hear you very well.
In this work, optimize by I'm sorry.
Maybe, sorry, Mr. Sami, maybe you better, you can try to switch off your video. Maybe
try again.
The transmission will improve. Okay, but now you are sharing a presentation.
The video. Yes, there is a delay in the audio, maybe.
Okay.
In this this presentation, the mechanics problems. This finite for this special this finite improve it. His displacement component with the shape.
I'm sorry, but
the stress field and of course the stiffness matrix.
We can hear you very well.
Yes.
Unfortunately.
Maybe I switch off the microphone from my computer. So
try.
So as I said,
no.
Yes, I adopted the and this closer is a two-step technique to open it. So it's first when the crack is opened and the displacement, and then the forces and the energy to close the crack. And for the stiffness derivative procedure, there is the energy of all the system, and then derivated by the displacement, the extension. Then we have the formulation of the energy release rate. To try this, the kinking is just one step of it's one to simulate a first its first direction with an angle theta. In this work there is a numerical example, a plate that is have loads and have the loads from above and up. Then it's have it's geometric, and it is an orthotropic plate with two different Young modulus in two directions, into two main directions. After simulating this plate, there is results that prove this element is quite in to I didn't before I didn't put the I didn't put the geometry, the simulation, the mesh. I don't know how I'm sharing it. I don't know if you say it, but conclusion, this Eisenhower modified quality of the mixed finite element can be obtained with to material rate. The first crack closure integral show better result on 3% error to 2.1%, and for the 0.7 to 3.4. That's all. Sorry for my bad and connection.
Okay, thank you. I'm really sorry that we missed a lot of your work, unfortunately. But it's I guess it's a matter of connection of network. Anyway, I might ask you, as you were considering kinking of cracks, which criterion did you use to determine the direction of a kinked crack?
Yes,
which was the criterion that you used?
Determined. Yes, I didn't use a criterion to study one special direction and angle. I simulated all of the angles and found all the energy release rates from them. I just simulate this plate as it is first. It have this will propagate in this direction theta, and I have found theta from 90 degrees to 0 degrees, from 90 to 0 degrees. That's
But why your crack kinks? Is it because you have a mixed mode?
I'm very sorry for the connection.
Condition, or
no? It is a mode 1. It is a mode 1 crack simulation.
Okay. But why, as is a mode 1 crack, you should have a coplanar propagation of the crack. So why are you considering kinking?
Yes.
Maybe something, because maybe I miss some point of your work.
Kinking. Yes, we want with my supervisor, we want to optimize this element to propagate to be as the XFMM in the would be the king. We won't only study the isotropic in which direction. So we hope that we can tell us in which way will propagate. So
okay,
it is the kinking.
Okay. Thank you for
hearing me.
Your work. Thank you. So we move to the final presentation of this session. Title is Effect of Impact Velocity and Friction on the In-Plane Crash Worthiness of Composite Plates, and will be presented in presence by Mr. Vigna. Okay. Please. Sì, qua. Questo possiamo. Questo lo con ricotta dell'Università di Padova? No, ridotta, no, ho preso lo distrutto. Ok. Okay, so please.
Good afternoon. I hope you can all see the screen, also from remote. I am Lorenzo Vigna. I'm a PhD student at Politecnico di Torino, and I will present this work carried out with Professors Bellingardi and Paolino from Politecnico di Torino, and with Andrea Calzolari and Giuseppe Galizia from Instron. Here we show the fixture that we designed to test the crashworthiness of flat composite plates. This fixture is necessary to avoid the debuckling of the specimen, and we use it in a drop tower testing machine to measure crash properties, between which the most important is the specific energy absorption of the material. Here you can see a video, an high-speed video of the test. As you can see, the load is applied on the top of the specimen as a falling weight, while on the lower part we have the crash of the specimen, and we acquire this kind of curve of force in time. This is the failure mode that the specimen shows after it is removed from the fixture after the test. So we can see that the lamination is the main failure mechanism, but the failures can show a bit different, like these two examples. Sometimes we have, like on the right, more deformation of the two foils, and sometimes we had a lower deformation of the foils with a more evident elastic return of the material. So what we first decided to do is to measure the deformation of the foils, and to do this we measured the angle between the two foils as a measurement of the deformation of the material. And we've seen that this angle is proportional to the specific energy absorption. That means higher angle, higher deformation of the material, higher specific energy absorption. After having used a correction to avoid this effect that was not related to the testing conditions, we found that the two factors that we were studying, the impact velocity and the crash clamping force, the first one, the impact velocity, had no effect on the result, on the specific energy absorption of the material, while the clamping force is influenced because of the friction between the specimen and the anti-buckling fixture. That's all from my side. If you have any question.
Luigi, if there are questions from remote, please. Otherwise, I can ask a question. You were in the impact that you were showing, the failure mechanism is basically a delamination. Okay, and
typical failure mechanism of crash boxes and other crash absorbers, specifically designed to absorb kinetic energy during crashes, and composites are very effective in doing this.
Okay. So the energy dissipated, from my understanding, is all related to the separation to the delamination process.
Yes, we have delamination and the formation of a lot of debris and powder, so fermentation as well.
Okay. No, because I was wondering, you were showing a picture where you are showing the angle of the opening angle after failure between the two lamina.
Yes, this was a strange effect that we found, and it was unexpected for us. Finding this kind of behavior, we would have expected similar behavior of the material. We think that it's due to material properties and typical variation of properties inside a sample.
But I was wondering if you were you could have looked also at the this curvature, this curvature of the two lamina as an indication of a dissipation, dissipated energy in the system.
We didn't consider the curvature, but only the angle, and we see that the angle is clearly influent.
Because probably the failure is very localized in this region.
Yes.
No. Okay. And maybe one final comment is maybe you can tell us something more regarding the testing equipment, because also the work is in collaboration with Instron, and it seems that there is something new in your testing system. Yes, what is the novelty of
this? This kind of test is completely new, non-standard. Several researchers have designed similar fixtures to test the flat plates in these conditions, but we designed a version to test in impact conditions, and this fixture is fully integrated with drop tower testing machines that for those that don't know, this machine is nothing more than a falling weight with known mass and speed, with a load cell that can acquire the force data that we used to calculate the energy absorption of the material.
But it seems from your results that there is no effect of the impact velocity.
No, there is no effect, and we can see from this plot that the impact velocity, at least in this range. Okay. What we have seen and is not shown in this presentation is that if we change testing condition, if we move to a quasi-static test, results can be quite different.
So probably what happens if you have a quasi-static condition, the SEA is lower, probably.
It's a bit higher.
Ah, yeah.
And we think it is due to the change in the friction coefficient in quasi-static condition, because also friction between the foils of the material and the lower plate is influent. I mean, from the movie we see the friction in this area. And that will be another field of our studies in next months.
Okay. So
thank you.
Thank you, Luigi, for your talk. And I think the session is nearly over, unless I can try again a final desperate tentative to see if two missing speakers are online. So I'm talking about the presentation entitled Evaluation of Driving Mode Progression Coupled with Overload Effect. Is one of the two authors online? No. And the other missing paper is Fracture Parameters of Alkaline Activated Aluminosilicate Composites with Ceramic Precursor, Durability Aspects. Is there any one of the speaker, of the authors connected online? No, I think we can stop here. So thank you all the speakers and the attendants for this session, and the conference will start again tomorrow morning at due time. Okay, thank you everybody. Bye, have a nice evening.
Thank you, the chairman.